Cool. So I'm Anthony. I'm a PhD student here at Otago. I'm supervised by Xiao and Michael Jack. And I've been looking at these things called hidden Markov models and how we can apply them to building energy consumption data. So we're talking about half-hour smart meter data here. We know that the energy consumption of each operating state is quite different from each other. So your states could be heating, cooling, or baseload only. So each of these has different characteristics, which would suggest that we want to model each of them differently. But when we look at the consumption data, we don't know what the building's doing at each of those times. So we want to be able to infer those states. This would suggest that a hidden Markov model could be a good candidate. So the key thing with these models is that they capture those underlying hidden states. So I'm going to talk more about what these hidden Markov models are, but first we need a bit of stats background. So what is a Markov process? We have a system that transitions between states where the future state only depends on the current state and not the previous history before that. So with the building energy example, we're going to consider two states. So the building could be occupied or unoccupied. And we're going to choose a time step to model that. So let's say hourly. And so for each hour, the building is going to be in one of these two states. And then when it's at the end of that hour, it's time to transition. And so let's say we're in the occupied state. We have a 0.9 chance of staying in that state. We have a 0.1 chance of moving. To illustrate how this would generate a sequence of states, we have another example. So let's call state 1 occupied, state 2 unoccupied. In this example, we start in state 2. It's going to stay with a probability of 0.7. It's going to move with a probability of 0.3. In this example, it moves to state 1. Now we're in state 1, so we stay with a probability of 0.9, move with a probability of 0.1. And so this process just carries on for as long as you want, and it generates a sequence of states over time. So that's a Markov process. So what is a hidden Markov process? We still have this same picture that we just saw. And now for each state, we're going to give it an emission function, which spits out a value. So these are distributions. Let's say state 1 has the distribution on the left, state 2 on the right. And then at each point in time, when you're in that state, you're going to spit out a value from the corresponding distribution. So we start, in this example, we start in state 2. So we spit out a value from state 2's emission function, gives 31.1. Then the underlying process carries on. We're now in state 1, so spit out a value from that function, 16.3. And this process carries on, your states keep changing, and you arrive with your observations on the right. In practice, the observations are the only thing that we can see with this. So we don't know what those emission functions are, and we don't know the underlying state. If we can structure a model where we have the correct number of states and say the correct shape of the emission functions, then if we give it the observations, we can infer what is going on underneath. So we can learn what those underlying transitions are. So at this point, we might be seeing where the application to building energy comes in. So those observations are going to be like your consumption data. And there is an existing model in the literature where it has a temperature dependence in those emission functions. The emission functions are normally distributed, so a bell curve with some width, and the mean of those emission functions are going to be linear dependence on temperature. And those dependences can be different for each state, so heating and cooling have different characteristics in relation to temperature, and so that's what we want to capture. It also has a temperature dependence in the transition probabilities. So we saw this kind of picture before, which just had numbers on it. Now we have functions of temperature. In terms of how the emission functions could depend on an external factor, this is what we saw before. Let's say that was fixed for, say, 20 degrees Celsius. And now if it's, say, 10 degrees, maybe you need more heating energy. So this whole picture might shift to the right to reflect that. And then in practice, we give it the historic consumption data and the temperature data, and then the model will infer all of those parameters during the model fitting process. So that's the existing model, and we've been looking at some potential improvements and extensions to that. So one extension could be a nested structure where we put one Markov process inside another. So that Markov process was the thing transitioning the states. So let's say we have the unoccupied and occupied states, the example that we had before, and let's put a new Markov process inside that occupied state, which describes whether the building is heating or not. And we saw in the existing model that it had a temperature dependence for the transition probabilities, but maybe we only want to apply that temperature dependence to the heating or not case. So we can, with this nested structure, we can easily control which transitions depend on which variables. Another potential extension would be incorporating time dependence into the model. So we can let those probabilities depend on time of day. And that dependence can be different. So you might have different behavior on weekends and weekdays. And if we use that nested structure, we could only apply that time dependence to say whether the building is occupied or not. Another extension could be incorporating solar gain, so how much heat energy from the sun comes in through the windows. We can do this in a similar way to temperature, and you'll notice that the solar gain term, so S, has a different sign in front of it, depending on whether you're heating or cooling. And this highlights why we want to be able to model each state in a different way. Solar gain isn't observable like temperature. So in the weather data, we have the solar gain received by a flat plane, but we want to calculate it for the actual building. So the model would need to infer the window size and orientation. So those were some potential extensions and some example results now. So this is a real building from Dunedin, so a commercial size building. We've got load on the y-axis and temperature on the x-axis. And I've modeled 3 states. So heating is that top cluster, unoccupied is the bottom cluster, and occupied but not heating is the middle cluster. And what the Hidden Markov model has done is it has inferred the most likely sequence of states, so those transitions that we saw, the most likely emission functions, and how they all relate to each other to give those observations that we saw. So it's inferred the most likely underlying sequence. And then this is how it's clustered those. So you'll see that there's some overlap in terms of clusters overlapping each other, which suggests that if you were to just plot this by itself, it would be difficult to extract those clusters. But the Hidden Markov model can do a better job. So to conclude, these models are a promising way of modeling the energy consumption. The key part of them is inferring that underlying state. And we've been looking at some extensions, including that nested structure, which has some major advantages. Thank you.
Great. Great, thank you. Any questions for Anthony? Any online? So you've got this in theory. Are you comparing the theory to actual building performance?
Yeah, so far we've tested it on some simulated data and also testing it on real data now. So that was the plot that we saw. So yeah, it's still looking for different data sources as well. Yep.
I don't think this isn't a question. I think it might be an offer. So would it be useful to have at least one house where we think, some relatively clean and robust division of those loads?
Yeah, exactly. So if we could have say the heating load separated out, then that could be really good for validating this kind of model.
Okay. Right, we need to have a think about that.
And cool. Yeah.
Cooling data as well. So if we can have heating, baseload, and cooling data, that would be, yeah.
What about charging? Yeah, yeah. I'm just thinking EVs.